All right, thank you for the introduction. So I'm here today to present the results of my research as a PhD student here on a talk titled Deep Data-Driven Modeling and Control of High-Dimensional Nonlinear Systems. All right, so I'll start the talk by just talking about dynamical systems. So a dynamical system is a system that evolves with time. And given that broad definition, there are many systems that can be classified as dynamical systems, ranging from the climate, financial markets, or robotics like drones. And a central focus in many domains of science and engineering is deriving models that describe the time evolution of these dynamical systems. And we want to derive these models because we can then use them for important tasks. One important task is prediction. So for example, in climate science, you might want to model for the Earth's climate so that you can predict how the climate will evolve over 20, 50, 100 years. Another important task is control. So in control, your goal is to select a set of control inputs in order to make a system behave in a desired way. So for example, making a rover on Mars go to a desired location. So given the usefulness of these models, there are some challenges that often arise when you try to construct models for real-world systems. And I've listed three important challenges here. So one challenge is nonlinearity. So many real-world dynamical systems are nonlinear. Nonlinear systems are harder to simulate than linear systems. And then on top of that, there are a lot of broadly applicable linear control techniques that don't necessarily apply to nonlinear systems. A second challenge is high dimensionality. So many real-world systems are high dimensional. For example, if you're constructing a climate model, you might want to model the time evolution of temperature measurements at thousands of ground stations around the globe. And if you're trying to describe the time evolution of that many quantities, it can be much harder than potentially just describing the time evolution of a relatively small number of quantities. And then the third challenge is that often the true dynamical models are unknown or expensive to evaluate. So generally, when we're constructing dynamics models, we might use knowledge of the underlying physics for a system in order to construct these models. But for something like a financial market, we don't actually know what those underlying physics, or the underlying physics don't exist. In other cases, we might actually know the model for a system, but actually evaluating that to high accuracy is very computationally expensive. So these challenges are kind of what have motivated my research. And the overall focus of my research is on trying to learn these models from data. So by taking, so given that we may not have these models that we can easily evaluate to describe how a system will evolve in time, we increasingly have the ability to store data that describes how they have evolved in time. And so by taking this data-driven approach, we can potentially learn models to describe any dynamical system for which we have data. On top of that, by using this data-driven approach, we can take advantage of very powerful learning techniques such as deep neural networks, which have shown the ability to learn complex nonlinear relationships from high-dimensional data such as image data. And then finally, by taking this data-driven approach, we can actually tailor our training procedures in order to give the learned models some desirable properties, such as low dimensionality for efficient evaluation or linearity for control. So the data that we will primarily focus on in this talk on learning from is computational fluid dynamics data. So computational fluid dynamics is a field that aims to approximately solve the governing equations for fluid flow. And CFD serves as a good test case for all of these techniques because it basically exhibits all of the challenges that I described earlier. So first of all, the underlying dynamics are nonlinear. Second of all, the simulations are often very high dimensional because it involves solving for flow quantities at many points within a mesh, like the one I've shown here. And then finally, the simulations themselves are actually very computationally expensive. So sometimes it can take hours or even days to run a simulation just for a single flow condition. So you can imagine if you're trying to iterate over many flow conditions in something like a design procedure, that can quickly become impractical. And just to show you an example for how large these simulations can scale, I have an example here of a simulation that Ph.D. ran. So this is a simulation of airflow over a turbine blade. And in the simulation, the system has over 100 billion degrees of freedom. And so simulating it required performing computations on 5,000 GPUs simultaneously on a supercomputer. And on top of that, each time snapshot in the system contains 105 gigabytes of data. So we won't necessarily work in this talk on any systems that are this size, but it does show you how big these things can scale and kind of motivates the design of these data-driven techniques. So with that, I'll now introduce the 4 contributions that my research has generated. The first contribution is on a multi-stage compression procedure to compress CFD data and reduce the storage overhead associated with running simulations like the one I just mentioned. The second contribution is on data-driven modeling and control of fluid flows. This is of interest because many the governing equations of fluid flows are nonlinear, which can make the design of flow controllers difficult. The third contribution extends the second contribution by giving the learned models a notion of uncertainty that it can use for control. And then the final contribution is on generative modeling of fluid flows, which allows for efficient simulation of fluid flows at many flow conditions. So in this talk, we'll actually only discuss the final three contributions, and I'll start with data-driven modeling and control of fluid flows. So everything I discuss in this part of the talk is summarized in a paper that I've listed here that was accepted at NeurIPS in 2018. All right, so the test case we're considering here is two-dimensional airflow over a cylinder at a Reynolds number of 50. Reynolds number is a quantity that captures the ratio of inertial to viscous forces in a fluid flow. And so changes in this Reynolds number are often associated with changes in the nature of a fluid flow. So in this case, at a Reynolds number of 50, that's right above the threshold where you transition from a steady flow that doesn't vary with time to this flow with vortex shedding. And this vortex shedding is associated with strong transverse forces acting on the structure. You generally see it not just on cylinders, but really in any kind of non-streamlined objects, so things like bridges, buildings, oil rigs, and so on. And so given its prevalence, it's been a system that's been studied quite a bit over the years, both experimentally and computationally. And in particular, people have looked into ways to potentially suppress this vortex shedding. And so given this prior work, the goal here is to present a method for learning a model for this system from data, and then use that model in order to design a controller for suppressing the vortex shedding. All right, so I mentioned we want to construct a dynamical model for this system, so I'll talk briefly about dynamical models. So in this goal, or in this section, our goal is to construct a dynamics model. So basically what it does is it describes how the state evolves from one time step to the next. You have this function f that advances the state forward in time. One of the simplest forms this model could take is that we assume the dynamics are linear. And in that case, we have an A matrix here that advances the state forward in time. So the first question I'll pose is that, say we assume that the dynamics are linear, but we don't know this value of the A matrix. How could we go about estimating that value? And what you could do is you could follow the procedure I've shown here. So you could take, in this case, if we're trying to model fluid flows, you could take a time snapshot of the system, take all of the flow quantities, so density, momentum, and energy at each point in space, and just stretch it out into a vector that we'll call x, and that'll represent the state vector of the system. Then we can construct two matrices, which I'll call capital X and capital Y, where capital X contains the states from time steps 1 through t-1, and matrix Y contains the states shifted by one time step. And then to estimate this A matrix that can advance these states forward in time, you can just do least squares to find the linear operator that approximately advances the system forward in time. Now, the problem with taking this approach is that it assumes the dynamics of the system are linear, when in fact they may not. And if your true dynamics are nonlinear, then this won't be a good fit to the dynamics of the system. So an alternative approach is, instead of saying that the states can be evolved forward in time with a linear operator, maybe we can find a state mapping, which we call g of x, where that can be advanced forward in time by a matrix A. We don't necessarily know what form this mapping should take, but we could potentially learn it with something like a neural network. But why would we assume that we could find a mapping like this at all? The reason for that is it lies in something called Koopman Theory. So Koopman Theory provides a method for mapping nonlinear systems to linear systems. And Koopman Theory basically says that there's a linear operator called the Koopman operator that can advance functions of the state forward in time. And so I have this diagram on the bottom that kind of illustrates the general idea here. So generally, for our dynamics, we have this function f, which may be nonlinear, that advances the state of the system forward in time. What the Koopman operator says is we can find this function g, which may be nonlinear, and construct a state mapping, g of x, and that can be advanced forward in time with this linear operator, the Koopman operator. And just some terminology I'll introduce now that will come up in the rest of the talk. We would generally call these functions, observable functions, and then the functions applied to the state observations. Okay, so in general, because this operator applies to all observable functions of the state, it's infinite dimensional, which limits its practicality or applicability. But under some conditions, it's possible to find a finite dimensional Koopman operator, under which case we've mapped a system with nonlinear dynamics to a system with finite dimensional linear dynamics. And so I have a quick example here that people often show to illustrate this idea. So we can consider this continuous time dynamical system. This is a nonlinear dynamical system because you have this x1 squared term. But we can define these three observable functions. So we can set g1 equals x1, g2 equals x2, and g3 equals x1 squared. And then when you evaluate the time derivative of all of these functions, what you can find is that all the time derivatives can be expressed as a linear combination of the observables themselves. And so what we end up with is this finite dimensional linear dynamical system that's kind of a transformation of this nonlinear dynamical system. So we can do it in this case because this is kind of a low dimensional system and it may be kind of obvious what these mappings should be to get these linear dynamics. But in general, we don't know the form of these observable functions. And so it's been something that's been the focus of a lot of studies, like how can you estimate or find these observable functions that give you these finite dimensional linear dynamics. So one approach that was proposed is from a NeurIPS paper in 2017. And basically what they propose is as follows. They say define a vector valued observable, which we'll call G, bold G. And then we can construct these two matrices x tilde and y tilde, which are similar to the matrices x and y that I defined before. But instead of having the states in the column of the matrices, now we have the observations, g of x. So we have these two matrices. And then what the paper showed is that the task of finding a finite dimensional Koopman operator is equivalent to the task of finding a state mapping, g of x, under which you can get a good least squares estimate for how to propagate the system forward in time. So you can do least squares on x tilde, y tilde, and find a matrix that can advance it forward in time accurately. And they proposed learning this mapping, g of x, with neural networks. And the training procedure they proposed looks something like this. So we can start with the matrices x and y, which I defined earlier, which contain your state values. Then you pass those values through an encoder neural network, which serves as the state mapping or outputs the observable functions. That yields these matrices x tilde and y tilde that I defined on the last slide. Then you can perform least squares with those matrices to get out a linear operator that can advance these observations forward in time. And then you pass everything through a decoder network that maps things back to the state space and inverts the original transformation. And so we can train all of the parameters in these two neural networks to minimize the loss I've shown here, which is basically a two-component loss. The first component enforces that the mapping that you learn is invertible. And then the second component enforces that when you perform this procedure, get out this A matrix, you can accurately approximate the dynamics of the system. And so this altogether represents a training procedure that we can use to map a nonlinear dynamical system and find a representation of the system under which the dynamics are finite dimensional and linear, or at least approximately linear. Now, one thing I haven't described is if we're going to train this on fluid flow, how do we actually represent the inputs that we pass into the network? And so what we decided to do is to represent the inputs as basically image-like inputs. So we look in the vicinity of the cylinder, and we find equispace points in a grid that's 128 by 256, where at each point we have 4 different flow quantities: the density, x momentum, y momentum, and energy. And then we can construct that as an input where it's like an image, but whereas an image would have red, green, and blue color channels, here we have 4 channels corresponding to the different flow quantities. And by constructing it in this way, we basically get to take advantage of all of the techniques and the architectures that have been created for neural networks to deal with image data in which they've achieved state-of-the-art performance. So this explains how we're representing the inputs to the network. We have our training procedure. Now I can show the results of actually training on modeling the dynamics of this two-dimensional cylinder system. So we have a visual comparison here that compares the x momentum and y momentum for the CFD simulation on the left and the neural network on the right. And so you can see visually, the neural network seems to be approximating the dynamics very well. And in fact, when you calculate the errors over time, the prediction error remains less than 0.2% across 128 time steps, which is approximately 8 periods of vortex shedding. So significant prediction horizon, the error remains low, and so this gives us confidence that in this case, it seems to have modeled the dynamics of the system well. But these aren't exactly the dynamics that we want to model because we're ultimately ended up in controlling this system to suppress vortex shedding. What we're ultimately interested in modeling is the force dynamics of the system, which means we need to introduce a control input that can actually affect the fluid flow. So the type of control input we decide to impart is rotation in the cylinder. So we can select a control input at each time step, which is a prescribed angular velocity on the surface of the cylinder. And then now, given the presence of these control inputs, we need a slightly different formulation for evolving the dynamics of these state mappings. And so we can do it with the equation I've shown here, where now we have this B matrix that governs the effect of the control inputs on the time evolution of the state mappings. And then we need now a procedure for jointly estimating A and B rather than just estimating the A matrix. And so if you work through the math, you can find that basically you can find it through this least squares procedure where you have this matrix Z tilde, which contains both the observations at each time step and the control inputs. Okay, so that's how we can train the network now to account for the effect of control inputs. So that means we can generate a training set and model the force dynamics of the system. Once we have that model, we actually want to apply a controller to suppress the vortex shedding. And so the way we go about suppressing the vortex shedding is through a model predictive control procedure. So at each time step, we solve the optimization problem that I'm showing here. That gives us a sequence of inputs that we should apply to the system. And we basically take the first control input in that sequence, apply it to the system, and then advance to the next time step. So because we have linear dynamics in this space of observations, this optimization procedure is a quadratic program which can be solved very efficiently. And so basically what the optimization problem consists of is we have an objective function that you want to minimize subject to some constraints, most notably that it respects the dynamics models that you've derived. The cost function, first of all, penalizes non-zero control inputs. And then we also need a way of encoding a measure of cost for the system. And so generally in a problem like this, you would say the cost is something like your distance from where you currently are to the goal state. So in this case, since we're working in this space of state mappings, we can define the goal state as the state mapping associated with the goal state. But one problem is that we don't actually know what the goal state looks like. We know we want to drive the system to a place where there's no vortex shedding, but we haven't actually done that, so we don't know what it looks like. So we need a way of representing this goal state. And so the way we decided to do that is I mentioned that we're simulating right over the threshold where you begin to see this vortex shedding. So if you go below that threshold, say at a Reynolds number of 45, you have steady flow that doesn't vary in time, which is what you're actually trying to drive this system to. And so we can take the steady flow at Reynolds number 45, feed that into our learned state mapping, and that gives us an encoding of the goal state, which we can then optimize in this model predictive control procedure. All right, so on this slide, I'm going to show the effects of performing this model predictive control procedure. In the top right of the figure, we're going to see an animation that shows what the x momentum of the system looks like over time. And then we're going to plot in the background the cost over time according to two measures. One measure in green is the cost that I just described. So this is the cost we're actually optimizing in the model predictive control procedure. And then the cost in blue is a separate cost. So that is the residuals from the CFD simulation. So the residuals correspond essentially to the time derivatives of the solution. And we expect those to be zero when we have a steady flow. And so if we can drive the residuals to zero, we would say we've achieved the task of suppressing vortex shedding. So this is essentially a way of viewing how well we're doing on a cost that we would like to optimize for if we could, but we can't necessarily frame that as a quadratic objective. And so I'll show the animation now. What you can see over time is that the vortex shedding is damped significantly. On top of that, if you look at cost measures, they both decrease over time, showing that the procedure appears to be effective. And also, most importantly, you can see that there's strong correspondence to between a decrease in the cost that we're actually optimizing for and the residuals, which is the cost that we would like to optimize for. So it gives us a sense that this objective that we're using is actually sensible for this problem. So one interesting thing we found is that when you look at the control inputs selected by model predictive control, you get something that looks like this. So this is plotting the control inputs over time in black. And then plotted over that is the y velocity measured at a point in the wake of the cylinder scaled by a value of 0.4. And so when you look at it in this light, it's what you see is that what MPC is doing is essentially functionally equivalent to just performing proportional control based on a measurement of the y velocity in the wake of the cylinder. And we actually thought this was pretty cool because if you look back at experimental results dating back to the 1960s, people are actually running experiments studying the effectiveness of using proportional control for suppressing vortex shedding for the cylinders. And so we've here done this data-driven procedure, run model predictive control, and then we've recovered this control law that people have been considering and thinking of using for many years. And so now that we have this control law, which is simple, easy to implement, the proportional control law, we can see if, okay, can we just perform proportional control to suppress vortex shedding? And so the point we identified is represented by D star here. And when you do use this proportional control law, you can see the residual over time, and you can see that it is effective at suppressing vortex shedding. But to illustrate that it's not just any proportional control law can suppress vortex shedding here, we also try performing proportional control with the same gains at different locations in the wake, and you can see that they're not at all effective at suppressing vortex shedding. And this aligns with other things in the literature, both experimental and numerical studies, which show that it is sensitive to both the measurement location and the gains. So to summarize, what we've done in this section is we presented a general method for learning linear dynamics for nonlinear dynamical systems. We've then used the learned models in model predictive control in order to successfully suppress vortex shedding. And then most importantly, by examining the selected control inputs, we actually recovered a simple, effective control law that's easy to implement. And so I really, as a high-level takeaway, I see this as potentially one of the benefits of doing these data-driven type approaches is that you can look at the way that they end up controlling the systems and maybe gain insight in how to design effective controllers when it might not be easy to otherwise gain that insight because they have nonlinear dynamics and they're very complex. Okay, so that concludes that section. We'll now move on to my next contribution, which is on uncertainty-aware modeling and control. And all of the results that I will present in this section was summarized in a paper that was presented at IJCAI just in August. All right, so one drawback with the approach for learning dynamics that I just described is that it gives us deterministic dynamics models. So there's no notion of uncertainty in the learned dynamics models that you get from modeling the system. And that can be a problem often with learned models if you're then trying to perform control, because if there are errors in the learned model, the controller might try might use that false information in a way that makes basically control less effective. And so generally what you want with a learned model is also for it to have some notion of uncertainty in its predictions for how a system will evolve in time, such that a controller can take that uncertainty into account in order to have more effective control. All right, so the main idea here is what we did in the last section is we actually modeled this observable function or the state mapping directly with a neural network. When you model that state mapping directly and you perform least squares, you get out a single A and B matrix with no notion of uncertainty encoded in it. What we do instead in this section is we try to infer the observations directly. So we try to infer distributions over G of X such that we get these distributions which we can then sample from. And then every time you sample from those distributions and perform least squares, you end up with a different A and B matrix. And so if you perform this sampling, say K times, you end up with K different linear dynamics models that can describe the time evolution of the system. And these linear dynamics models then perform essentially form an ensemble of models that you can use to use as a measure of the uncertainty for how this system will evolve in time. So just to kind of illustrate what we're doing here a little further, imagine we're trying to model the time evolution of a pendulum system. So this is cosine theta, sine theta, theta dot. The black line shows the true time evolution of the system over time. We may sample one dynamics model that predicts the system will evolve like this. We may sample a second model that predicts it will evolve like this. If we sample 10 models, we get a range of predictions. And then if we sample many, many models, we get something like what that looks like this, where the blue region basically captures the range of predictions across all sampled models. Okay, so how do we actually formulate this problem? Again, I mentioned we're trying to infer the value of these observations, g of x, which we do not know. So we represent the observations as a latent variable, which we call g sub t. In addition, we introduce a second set of latent variables, z1 through t, which basically enforce that once we sample from these inferred distributions and construct our dynamics models, we can actually accurately model the dynamics of the system using that sampled model. And then finally, we assume we can recover the state of the system by then inverting the observable functions. So we do g inverse on the latent state z sub t. And then the goal here is ultimately to infer the underlying observations that maximize the likelihood of an observed trajectory. So it's the probability of the observed states conditioned on the actions, which in reality involves marginalizing over the latent states g and z. So actually optimizing for this objective directly is generally intractable because it requires performing this marginalization, but we can rely on variational inference to derive a lower bound on this objective, which we can optimize. And so skipping a few steps of math, I'll just present the lower bound here. And just to summarize, what we see here is basically two types of objectives. We see likelihood objectives, which are the likelihood of the states conditioned on the latent variables. And then we have these KL divergence terms, which represent the KL divergence between the inferred distributions and prior distributions P. And so we can train a model to optimize this lower bound. We call those models deep variational Koopman models. Uh-oh. Uh-oh. All right, I won't touch it again. There we go. All right, we're back. We call these deep variational Koopman models. And so basically, we can train these models on data that contains state and action values. And then given a new trajectory of state and action values, we can use this to infer the distribution such that we can sample an ensemble of linear models that describe the time evolution of the system. So we do some experiments to test how good this is at both modeling dynamics and also some control experiments as well. In this part of the talk, we focus primarily or exclusively on low-dimensional systems, and we do this because it's easier to visualize for these low-dimensional systems whether you're getting reasonable uncertainty estimates than it is for high-dimensional systems. So the three systems we consider are the pendulum, the cart pole, and the acrobat. Oh my God. Do you know, should I touch this? Yeah. Do we need Shishman to watch this again? Yeah. It says system shutting down. Should I do some whiteboarding? Yeah. It'll take about 45 seconds. I thought you were going to say 45 minutes. I guess it's been on for like a couple of hours. Probably. Oh, is that how it works? Yeah. 20 minutes? Okay. Okay. Here we go. I don't know. Do you think that was the problem? Does someone need to sit here and? Okay. All right. Um, all right. So yeah. So these are kind of three classic cart pull and acrobat or double pendulum. And so the first experiments we ran were just to see how well it could model the dynamics of these systems. And so we have first some qualitative results that show that here. So this is showing the time evolution of the double pendulum system across all state values. The true state values are shown in black. And then the range of predictions across all sampled models are shown in blue. And so you can see that the models appear to be modeling the dynamics of the system accurately, with kind of reasonable uncertainty estimates, kind of higher uncertainty near the minimums or maximums in the time evolution. I should mention that we're simulating this system for 128 time steps, but we only allow the model access to information from the first 64 time steps. So it's basically predicting the time evolution of this system for the final 64 time steps, which is good because what we want is to ultimately use this for control, where it needs to be able to predict how the system will evolve in future unobserved time steps. So we did kind of more quantitative summary of performance. So we compared it against three baseline models in terms of prediction error and negative log likelihood. And without going into too much detail here, the high-level summary is our models, the deep variational Koopman models, perform essentially on par with or better than all of the baseline models, while offering some benefits such as providing linear dynamics models that are useful for control. And speaking of control, so the control problem we evaluated on is a kind of classic control problem, which is inverted pendulum. So the goal in this task is to balance a pendulum vertically. And you have a cost function at each time step, which is what you see here, which basically penalizes deviations from vertical and also non-zero angular velocities and control inputs. So in order to perform control, we use an algorithm called differential dynamic programming, which allows us to optimize a sequence of actions. And then we also perform model predictive control once again. So we get this action sequence from differential dynamic programming, execute the first action, and then replan at the next time step. So that's kind of the overall summary, but there are a few things we need to discuss about how we actually go about incorporating these learned models into differential dynamic programming. So one thing is, how do we actually represent the cost that we're optimizing for? Because we have these linear dynamics models, but they're actually linear in this latent space, not in the state space, but we have a cost that's defined in the state space. And so we need to somehow map that cost into the latent space so that we can optimize it for it. One option is to do what we did in the last section, where you find basically like an encoding associated with the goal state and measure the cost as the distance from that. But in general, that is not something that you might expect to work, because there could be similar latent encodings to two states that have very different costs. So what we do instead is we actually form an approximate quadratic cost in the latent space by finding the gradient and the Hessian of the cost with respect to the latent state. And then you can form this approximate quadratic cost, which can then be incorporated directly into the DDP algorithm to optimize the action sequence. Second thing we need to talk about is the fact that DDP assumes that you only have a single dynamics model, but here we have potentially many dynamics models. And so how do we take into account the range of predictions across these dynamics models in order to optimize the action sequence? And so we kind of consider two procedures for doing this. One procedure is expected cost, and one is worst case cost. So in the expected cost, we essentially form dynamics where we can propagate the dynamics jointly across all models, and then find the average expected cost across all models. And then we can optimize for that. Under worst case costs, we actually find for a given action sequence the model that predicts the highest cost, and then optimize for that model, and then find a new action sequence, find the worst case cost, or the model predicting the worst cost, and so on. So those are the two optimization procedures we considered. And so now I can just walk you through how you go about then training one of these models and using it for control. So in the simulations I'm about to show here, we basically started by training a model on 20 trials where the system was subjected to random control inputs. And then once you had a trained model, you can then incorporate it in model predictive control in 2 trials, which I'm showing here. And so basically what you can see is that the MPC procedure is maybe capable of swinging up the pendulums, but not so good at balancing. And that's likely because it hasn't seen much data for how the system behaves near the goal state. But you can take the data from these trials, incorporate that into the training data, train the model again, and then evaluate again in trials. And so when you do that a few times, after a few trials, you can see that now the pendulum is able to swing up, or the MPC is able to swing up and balance the pendulum. If you run it 2 more times, you can see it works again. But what we care about more than just how it performs in a few trials is how it performs across many trials, and how the number of sampled models and the different optimization procedures actually affect your performance. And so what I'm showing in this table here is showing the performance on this inverted pendulum task as you vary the number of sampled models and optimize using either this worst case or expected cost procedure. And the 3 metrics we consider are cost, so this is just the average cost per trial. The fraction of time vertical, that's the fraction of the time in each trial that the pendulum spends in the interval minus pi over 8 to pi over 8. And then falls per trial is the number of times per trial where the pendulum is in the interval minus pi over 8 to pi over 8 for more than 20 seconds and then leaves. So it has it balanced and then loses it. And so by looking at these results here, you can see a few trends. So one important takeaway is that you see generally or across the board improving performance with the number of sampled models. On top of that, the model with the best performance appears to be the procedure with 30 sampled models, optimizing for worst case cost. But you can also notice that for lower numbers of sampled models, the expected cost procedure performs well. So maybe if the goal is to get better control performance with fewer sampled models, expected cost is preferable. So to summarize the takeaways from this section, what we did is we presented this deep variational Koopman model, which is a method for uncertainty-aware dynamics modeling and control. The models were shown to accurately model the study dynamical systems and provide reasonable uncertainty estimates. And then in a control setting, we demonstrated that sampling more models appeared to lead to more or better control performance. All right, so that concludes the discussion of that contribution, which now leads us to the final contribution on generative modeling of fluid flows. So I'm going to start this section by once again putting up this objective for the deep variational Koopman model. If you remember what I said is there are kind of 2 types of objectives in here. There's the likelihood objectives, and then there's the KL divergence objectives, where the KL divergence is between the approximate posterior distribution Q and the prior distributions that don't depend on the states. And so if you can optimize this lower bound well, then the KL divergence between the approximate posterior and the prior distribution will become small, so those distributions will become similar. And then what you can do under those circumstances is potentially deploy the model in a generative fashion, where you sample directly from the prior distributions. And in doing so, you can generate data that looks as if it was drawn from the same distribution as the data that you trained the model on. And in particular, in this section, what we're considering is an objective of this form, where instead of conditioning on the actions over time, we're now conditioning on a parameter vector C, where C contains basically a definition of flow parameters to be varied. And so you can train a model to optimize this objective on fluid flow data taken with different flow parameters, and then potentially deploy the model in a generative fashion where you specify first a flow parameter C and then sample a model corresponding to those flow conditions. So for example, you specify Reynolds number 50, sample fluid flow at a Reynolds number of 50. And so given that there's often a high cost with running CFD simulations at many flow conditions, you can potentially use these generative models by first running CFD simulations at basically a handful of flow conditions, training a model on that data, and then have the ability to sample fluid flow both at the flow conditions contained with the training data, but also in other flow conditions as well. So the test case that we test this on is now a system with 2 cylinders. So it's airflow over 2 counter-rotating cylinders. This is a test case that was studied extensively by someone named Andy Chan, who got his Ph.D. in Professor Jameson's lab in 2012. So the scenario here is we have these cylinders. Once again, you see vortex shedding over the cylinders. And you can apply this rotation speed omega to the cylinders, and it's assumed that that rotation speed remains fixed within a simulation, but can vary across simulations. And so this rotation speed can have kind of a pretty significant effect on the overall nature of the fluid flow. We show four animations here that show the effect of this rotation speed on the fluid flow. So at rotation speed of 0, you can see this vortex shedding similar to what we saw earlier in the talk. And as you increase the rotation speed, you can see the nature of the flow changing up to the point where at a rotation speed of 2, you now have steady flow that's not varying with time. Another way to visualize these effects is to look at the lift force over time on the upper and lower surfaces of on the upper and lower cylinders. And so that's what these plots show for different rotation speeds. And what you can see is as the rotation speed increases, the lift curves separate, and then ultimately you end up with these flat curves that don't vary with time. And so we would say by looking at these plots that somewhere between rotation speed of 1.75 and 2, we've reached a critical rotation speed where we've transitioned from having unsteady flow that varies with time to having steady flow that doesn't vary with time. And then we just have this constant transverse loading on these cylinders. So this is one parameter that can affect the nature of the fluid flow. Another parameter that can affect the nature of the fluid flow is the Reynolds number. And so these animations show the effect of varying the Reynolds number on how the cylinder system varies with time. So you can see that as the Reynolds number increases, notably the period of vortex shedding increases. And there are other kind of qualitative differences in the flow. So now we basically have two parameters that we can vary that can then alter the nature of these flow fields. And so this is kind of the test case that we consider testing out this generative modeling procedure. And so we can generate training data for this generative model to train on. We can generate it at a series of flow conditions, which I've listed here. So Reynolds numbers of 75, 85, 100, 125, 150, and 200. And then rotation speeds in increments of 0.25 between 0 and 2.5. And so all of the locations where we've run these simulations, I show in this figure here where we're plotting Reynolds number against omega. So those are the black dots. But what we're hoping we can do is by training on this data at those locations, we can actually generate accurate fluid flow anywhere in this domain in the purple square here. So actually training on this data takes about 30 hours. So there is a big upfront cost in terms of training it, but you get a very large speed up from the trained models. So once you deploy the models in a generative fashion, simulating the fluid flow with the generative model is about 120 times faster than simulating it with a CFD solver. But of course, what we care about is not just if we can simulate it faster, but whether the simulations are actually accurate. So in the next few slides, I'll show kind of some visualizations of the fluid flow that give a qualitative sense for how well it is at approximating the fluid flow. So starting with Reynolds number 150 and a rotation speed of 0. So we're showing on the left the CFD simulation, and on the right the generated solutions. And this is looking at density, x velocity, y velocity, and pressure over time. And you can see when you compare both the CFD and the generated flow that there's a lot of qualitative similarities between the two. We can also check if it can model the effects of changing the rotation speed. So we can consider fluid flow at Reynolds number 150, rotation speed of 1. And you can see here that the generative model, again, captures the change in the nature of the flow. We can also vary the Reynolds number. So this shows Reynolds number 75, rotation speed of 0. You can see, again, the generative model does well at modeling the nature of the flow. But most importantly, we can also run a simulation at Reynolds number 175, rotation speed of 1. This is at flow conditions that aren't contained in the training data. And yet, when you compare the two flows, they do appear to be similar. And so this shows that we have the ability to simulate not just the flow conditions contained within the training data, but also other flow conditions, or at least gives us the sense that we might be able to. So what I've shown so far is just kind of global simulation, like visualizations of the simulation, where they kind of look qualitatively similar. But what we also care about is whether locally it does a good job of capturing the time evolution of the fluid flow. So on the next few slides, I will show plots that demonstrate how the generated flows model the time variation of the flow quantities at the point that I've defined here. So it's in the wake of the top cylinder, and you would expect to have some interesting behavior. So what these plots show is on the left, the pressure values plotted over time for different rotation speeds for the CFD data. And then on the right, we have the corresponding generated solutions at the different rotation speeds. And so you can see, for example, if you look at the difference between rotation speed of 0 and 1.75, there's a big qualitative difference between the two. And when you look at the generated solutions, it seems to capture pretty well that variation in performance. This is again showing pressure values over time. You can also look at Y velocity values over time. And again, see there's big variation in the CFD simulations as you vary the rotation speed, and the generated solutions are able to capture that very well. We can kind of use a more quantitative approach to see how well it's actually capturing the time evolution of these quantities. So what we do in the next experiments is we look at the frequency content of the true and generated signals. So this shows the density over time for one of the flow conditions, and the corresponding power spectral density is shown here on the right. And so you can see there are a few different peaks in the signal, but there's one peak that's larger. And so basically what we do in these experiments is we look at how this frequency associated with the largest peak in the signal varies as you vary these flow conditions and vary the flow quantities that you're modeling. And so we have the results for that on the next two slides. So this is showing on the left for density, plotting this frequency associated with the maximum peak as a function of Reynolds number at the different rotation speeds. The CFD values are shown in blue, and the generated values are shown in red. On the right, we're looking at the x velocity values over as a function of Reynolds number. And then finally, on this slide, we're showing y velocity and pressure. And basically, if you look at the relative errors across all flow conditions and all flow quantities, you find that the relative errors are less than 1.2%. So it seems like we're modeling the behavior of the system at this point pretty well. So this gives us some confidence that these simulations are actually modeling this fluid flow accurately. And so now we can try to use this generative model in a way where we basically run many simulations rapidly in order to kind of evaluate the nature of the flow of the system. This kind of mirrors what you would do in a design procedure where you would maybe want to sweep over different design parameters and identify spaces in the parameter space that correspond to your design objectives. So in this case, what we consider is sweeping across these parameters, rotation speed and Reynolds number, and trying to identify where within this domain as a function of Reynolds number you see this critical rotation speed. So the rotation speed where you transition from the unsteady flow to the steady flow. And so because these generated solutions are relatively efficient to run, we just run a bunch of simulations. So we run them at Reynolds numbers of 75, 76, 77, and so on up to 200. We run them at rotation speeds of 1.1, 1.11, and so on up to 2.1. So we run a bunch of simulations. It takes about 10 hours to generate all those solutions, which is not insignificant, but it is much less than what would be required to run it with CFD, which would be nearly 2 months. Okay, and then once we've run these simulations, we can actually look at the generated solutions in order to evaluate where these critical rotation speeds might be located. So what I've shown on this plot is that behavior for a fixed Reynolds number as you vary the rotation speed. And what we're plotting is the norm of the time derivative as you vary the rotation speed for a fixed Reynolds number. So you would assume that once you reach this critical rotation speed, the flow does not vary with time, so you'd expect the time derivative to be 0. So this quantity, taking the norm of the time derivative in the generated solutions, that basically gives us a way of measuring how close we are to this steady flow and identifying this critical rotation speed. And so you can see that eventually we do reach a point where this time derivative is low. And on top of that, we kind of have this smooth decrease and then kind of a sharp drop. And so we would say the critical rotation speed is probably somewhere in this region. Because there's kind of this smooth variation, it's a little hard to say what exactly we should define as being the critical rotation speed. And it may be kind of sensitive to what threshold we use. And so what we did is just define two thresholds and say this kind of defines a range of plausible rotation speed values within which we think these critical rotation speeds might lie. And so we can do this as a function of Reynolds number and then give us these plausible ranges for Reynolds numbers where we think this critical rotation speed occurs. And so once we do that, we can take this original domain, which looks like this, and we can narrow it down to a region that's much smaller. And then I actually ran a bisection search at a handful of Reynolds numbers to actually identify with the CFD simulations what the true critical rotation speeds are, and those are plotted with the x's that we show here. And so you can see that they're all within this region of plausible rotation speeds that we've identified, which gives us a sense that we did an accurate job of identifying this area of the parameter space. All right, so the last experiment we wanted to do with the generative model is actually see how well it can scale. So we just modeled a two-dimensional flow. Now we look at modeling three-dimensional turbulent flow. So this is airflow over a cylinder again. What we're looking at here is basically two different ways of visualizing the same fluid flow. On the left, we're looking at isocontours of the Q criterion. So that's a criteria that's often used to kind of visualize the presence of vortical structures in the flow. And then on the right, we're seeing isocontours of vorticity magnitude colored according to pressure. And here, we're just considering varying the Reynolds number, so we don't have any rotation speed or anything like that. And we're also not going to do like a heavy quantitative analysis of this. We just want to see qualitatively, can it scale to potentially modeling fluid flows like this. And so we have data generated at Reynolds numbers 175 and 200, as well as 250 and 300. And you can see by the time you get to this flow at Reynolds number 300, there's a large amount of turbulence in the wake of the cylinder, which is potentially very difficult to model. And so on the next few slides, I now have a visual comparison of the generated flow at each one of these Reynolds numbers with the CFD generated flow. So this is Reynolds number 175. And you can see, again, there's a little noise in these isocontours that we're extracting, but generally it looks very similar to the CFD flow, or CFD generated flow. You see the same result at Reynolds number of 200, the same result at Reynolds number of 250, and even at Reynolds number of 300, you see it generating flows with a large amount of turbulence in the wake of the cylinder. And I should point out that all of these isocontours are extracted based on the spatial gradients of the velocity field, which are approximated with finite difference. So it's very sensitive to any errors in the velocity field. So to even have these vortical structures show up in the first place is difficult. And then to have this kind of temporal coherence in the generated flow where the vortical structures remain from one time step to the next and are propagated downstream, I think is pretty impressive. All right, so to summarize, what we've done in this section is presented a method for generative modeling of fluid flows conditioned on flow parameters that allows for efficient simulation at many flow conditions. The generated simulations are about 120 times faster than the corresponding CFD simulations in both the 2D and the 3D case, allowing for rapid simulation at multiple flow conditions. And finally, the scalability of the approach was tested by applying it to three-dimensional turbulent flows. So that concludes the three contributions of the talk. So I'll just summarize what those were again. So it was data-driven modeling and control of fluid flows, data-driven modeling and control with uncertainty, and then finally, generative modeling of fluid flows. In terms of future work, I just left it to, I mean, there's many extensions to all this work, but I just wanted to list three that I think are most important, especially this first one. So all of the work that I have shown here was basically modeling these systems in equation-free context. So we don't use any knowledge of the governing equations of these systems as we're trying to learn those dynamics. And that's appealing in some sense because it allows you to potentially model any type of system. The methods are very general. But I think in general, it's also very important that if we have knowledge about how a system behaves, and a lot of us here are aerospace engineers and spend a lot of time learning how to model these systems, I think it's important to try to design learning algorithms that can take that knowledge into account. And there have been some interesting papers already, but I think there's a lot of interesting work left to do in that area. Another important extension would be for the dynamics modeling parts, accounting for measurement noise and stochasticity in the dynamics. And then finally, just to make these methods that are applied to CFD more general and maybe scale it to the type of simulations that Freddie ran on the turbine blade, things like scaling up to larger problems, dealing better with unstructured grids, dealing with simulations where the geometry changes from one simulation to the next. These are all kind of challenges that need to be addressed. These are a list of my publications. So the ones related to the work that I'm presenting here are highlighted in black, and then some of the prior work on driver modeling is here as well.